Namaskar, my dear friends. Welcome to the lecture series of machine design. In our previous video, you will learn about the design of crankshaft, okay, uh, center crankshaft and side crankshaft at a top dead center position. Okay. Now, in this lecture, we are going to learn about the design of side crankshaft at angle of maximum torque. Okay, so the torque is maximum when the tangential component of the force on the crank pin is maximum. Okay, so for this condition, the crank angle from the top dead center position theta is usually 25° to 35° for petrol engine and 30° to 40° for diesel engines. Okay, so before the design procedure, let us uh, understand the assumptions made for this design. So it is assumed that the engine is vertical, okay, and the belt drive is horizontal, and the crankshaft is simply supported on bearing 1 and 2. Now let us see here. You can see side crankshaft, okay, which is supported at this bearing 1 and bearing 2, okay, and you can see the center load W is acting in this direction, downward direction, and load due to the belt tension, okay, T1 and T2, the load is P1 plus P2 is acting on the horizontal plane. Okay. Now here you can see the distance between the two bearing is C. Okay, distance between the two bearing is C, and distance between the bearing 1 and this load W is C1. Okay, and distance between the bearing 2 and load W is C2. Okay, now here you can see at this crank pin, okay, the load PQ is acting in this direction. Okay, thrust PQ is the thrust on the connecting rod. So due to that, there are two components. This PR is the radial component of the force on the crank pin. Here you can see the PR is a radial component of force on the crank pin. Okay, PP is the force acting on piston top due to the gas pressure is PP, and PQ is a thrust on connecting rod. So there are two components of this PQ. One is the PT. PT is the tangential component. Here you can see this is the PT. PT is the tangential component of force on crank pin, and PR, this is the PR. PR is the radial component of force on crank pin. Okay, and phi is the angle of inclination of connecting rod with the line of dead center in degree, and theta is the angle of inclination of crank with line of dead center. Okay, now here you can see the different reactions due to this load W and P1 plus P2. You can see the different reaction acting at the bearing 1 and bearing 2. Okay, so you can see this R1V. Okay, R1V is the vertical reaction at the bearing 1. R1H is the horizontal reaction due to this load P1 plus P2. Okay, so similarly R1 dash V and R1 dash H, and this R1 is the total reaction at the bearing 1. Okay, similarly here you can see this R2V and R2H and R2 dash V and R2 dash H. Okay, so these are the different reactions acting at the two bearing 1 and bearing 2, right? Now here you can see this figure A, okay, which shows the vertical plane, and this figure B, which shows the horizontal plane. Okay, and here you can see the different reactions right? At the in vertical plane, you can see this is R1V at the bearing 1 and R2V vertical reactions at the bearing 2, and distance between these two is C. And here this PR, okay, PR is the vertical load, you can see here, so PR, and the distance, okay, this distance is B. Okay, this is the overhang. B is the overhang. Okay, and this distance is B. And here you can see it is the 0.75 LC. The load is acting from here. It is 0.75 LC. Now here you can see the load R1 dash V. Okay, and R2 dash V and load W, and distance is C1 and C2. Similarly, in the horizontal plane, you can see R1H. Okay, and here it is the R2H. You can see here R2H. Okay, and this load is PR. Okay, similarly here this load is P1 plus P2 and R1 dash H, R2 dash H. Okay, so these are the different reactions in different position. Okay, now let us understand the component of force on crank pin. Okay, component of force on crank pins. So suppose P dash is the gas pressure. You can see the P dash. P dash is the gas pressure on the piston top for the maximum torque condition. So we know that the load on the piston top PP, okay, is equal to area into pressure. Okay, so this area is pi by 4 d square, and pressure is the P dash, right? And the relationship between this phi and theta. Okay, you know that what is the phi? Phi is what? Angle of inclination of connecting rod with the line of dead center. Okay, angle of, you can see here, this is the angle of inclination of connecting rod with the dead center. This angle is known as a phi. Okay, and the theta is the angle of inclination of crank with line of dead center. Okay, angle of inclination of crank. Okay, this is the theta. So relation between these two, phi and theta, is given by sine phi is equal to sine theta upon L by R. Okay, so this L by R is a ratio of length of connecting rod to the radius of crank. Okay, L by R is the ratio of length of connecting rod to the radius of the crank. Now, the thrust on connecting rod PQ. PQ is the thrust on connecting rod which acting on this direction. You can see here in this figure, this thrust load PQ. Okay, so the value of this thrust load PQ is given by PP upon cos phi, right? PP upon cos phi. Now, there's two components, the tangential and radial component, okay, of this PQ at the crank pin. Okay, so it will be given by this equation. PT is equal to PQ sine theta plus phi, and PR is equal to PQ cos theta plus phi. Okay, so different components of force on the crank pin is given by this equation. Okay, PT, PR, and PQ. Now let us find the bearing reactions. Okay, different bearing reactions. Okay, so the forces acting on the side crankshaft at an angle of maximum torque are, we have seen already in the figure. Okay, the reactions are like this. Okay, so vertical and horizontal reactions. So the crankshaft is, we know that supported on two bearings, 1 and 2, right? So now the forces in vertical plane. Okay, so the reaction of PR. Okay, reaction of PR. So R1V and R2V are the reactions at bearings due to the radial component PR. Okay, so for that, the taking moment of forces about about the bearing 2. Okay, about the bearing 2, the PR is the load. Okay, so the PR into distance what? B plus C is equal to R1V into C. You can see. So PR into B plus C, R1V into C. So therefore, the R1V, okay, R1V is equal to PR into B plus C upon C. Okay. Now taking moment of forces about the bearing 1. Okay, about the bearing 1. So for that you can see the PR into B. Okay, PR into B is equal to R2V into C. So therefore PR into B into R2V into C. So therefore reaction R2V is given by PR into B by C. Okay, equation A and equation B. So you can find the R1V from this equation and R2V from this equation. Now reactions of W. Okay, so R1 dash V and R2 dash V. Both are the reactions at bearing due to the weight W. Okay, so taking moment of forces about the bearing 2. Okay, so due to that this load W. Okay, so taking moment about this. So therefore R1 dash V into C, total C1 plus C2 C into is equal to W into C2. So W into C2 is equal to R1 dash V into C. Therefore, you can find R1 dash V is equal to W into C2 by C. Now, taking moment of forces about the bearing 1. Okay, now take the moment of forces about the bearing 1. So therefore, we can say R2 dash V into C is equal to W into C1. Okay, so moment of this and this about the bearing 1 here. So therefore W into C1 is equal to R2 dash V into C. Therefore R2 dash V is equal to W into C1 by C. So from equation C you can find the value of R1 dash V, and from this equation D you can find the value of R2 dash V. Okay, so these are the different bearing reactions you can find, okay, from this equation A to D. Now horizontal forces in horizontal plane. Okay, so the reaction of PT, similarly we can see from figure 2, figure B. Okay, reactions of PT. So R1H and R2H are reactions at bearing due to tangential component PT. Okay, so therefore taking moment about here tangential component. Okay, so you can horizontal reactions. So PT into B plus C is equal to R1H into C. Therefore R1H is equal to PT into B plus C by C. So you can find the horizontal reaction R1H at bearing 1. Okay, from this equation E. Similarly, taking moment of forces about the bearing 1. So PT into B is equal to R2H into C. So therefore R2H. So horizontal reaction at bearing 2 is PT into B by C. Okay, so you can find the R2H from this equation F. Now reactions of P1 plus P2. Okay, due to the load this P1 plus P2, and due to this P1 plus P2 the reactions are R1 dash H and R2 dash H. Okay, so this is R1 dash H and R2 dash H. So reaction due to the P1 plus P2. So by taking the moment about the bearing 2, we can say R1 dash H into C is equal to P1 plus P2 into C1, and taking moment about the bearing 1, we can say R2 dash H into C is equal to P1 plus P2 into C1. Okay, so therefore taking moment about the bearing 2, you can say P1 plus P2 into C2 is equal to R1 dash H into C. So therefore R1 dash H is equal to P1 plus P2 into C2 by C. Okay, and taking moment of forces about bearing 1, you can say P1 plus P2 into C1 is equal to R1 dash H into C. So therefore R2 dash H is equal to P1 plus P2 into C1 by C, equation H. So from equation A to H, okay, A, B, C, D, E, F, G, H, A to H, you can find all the reactions acting at the bearing 1 and 2, right? Now, in next step, let us find uh, this design of crank pin. Okay, so we have already discussed in our previous, okay, that the load on the crank pin, okay, it acts at a distance of 0.75 LC, right? So from the crank web, okay? So we can say, or we will assume the force components that PR and PT, they act at a distance of 0.75 LC, 0.75 LC from the crank wave. So the crank pin, which is act as a cantilever and subjected to the maximum bending moment at the crank wave. So the bending moment in the vertical plane, okay, is given by MBV is equal to PR and the distance is 0.75 LC. Okay, now similarly, the bending moment in the horizontal plane is MBH is equal to PT into 0.75 LC, right? So the resultant bending moment MB, the resultant bending moment MB is given by root MBV square plus MBH square. Now we know that the sigma B is equal to M by Z. Okay, sigma B is equal to M by Z. And Z is the section modulus. So therefore Z is equal to pi by 32 DC cube, where DC is a diameter of the crank pin, right? So therefore MB is equal to sigma B into pi by 32 DC cube. So the bending stress finding from this equation, okay, sigma B, okay, so that value of the sigma B, okay, is it's calculated from this equation, and it should be within the permissible limit. Okay, it should be within permissible limits. So from this way you can find the crank pin diameter. Now next step is design of crank wave. Okay, so crank wave design. So as shown in the figure here, right? Crank wave, here you can see the its thickness is T, width is B. Okay, so for that the different assumptions, bending stress in vertical and horizontal planes due to the radial component PR and tangential component PT. Okay, bending stress in vertical and horizontal plane due to the two component PR and PT respectively, and direct compressive stress due to radial component PR and torsional shear stress due to tangential component PT. Okay, because it is the eccentric load. So due to the eccentric load, there are two types of the stress. One is the bending and another one is the direct compressive stress. Okay, so now bending moment due to the radial component. Okay, so the bending moment due to radial component at the central plane, which is given by, here you can see MBR, okay, is equal to PR into 0.75 LC plus 1 by 2 T. Okay, so 0.5 T, and Z is the section modulus. So Z is equal to WT square by 6. Okay. Now we know that the moment is equal to MBR is equal to bending stress due to the radial component sigma BR into Z section modulus. So therefore we can say sigma BR into 1 by 6 WT square. Okay, so MBR is equal to sigma BR 1 by 6 WT square. Now the bending stress due to the radial component is calculated by this equation. Now the bending moment due to the tangential component. Let us find the bending moment due to the tangential component at the juncture of this crank wave and shaft. Okay, is given by this equation due to the tangential component MBT is equal to PT R minus D1 by 2, where D1 is the diameter of shaft at the juncture of crank wave. And as usual, you know that the Z is equal to 1 by 6 TW square. So therefore, moment due to the tangential component sigma BT into Z. Okay, so put the value of Z. So MBT is given by sigma BT 1 by 6 TW square. Okay, so now the bending stress due to the tangential component is found from this equation, right? Now the direct compressive stress due to the radial component. Okay, so the direct compressive stress due to the radial component sigma CD is equal to PR radial component and W2 is the area, W into T, width into thickness. So maximum compressive stress is given by sigma BR plus sigma BT plus sigma CD. Okay. Then the torsional moment on the arm, okay, torque on the arm, MT is equal to PT into 0.75 LC plus 0.5 T. Now shear stress tau is equal to M by Z. Okay, ZP is the polar moment, polar section modulus. So therefore it is given by, okay, this ZP value of the ZP is equal to WT square upon 4.5. So therefore put the value here 4.5 MT by WT square. Okay, so therefore sigma C maximum is given by sigma C by 2 plus 1 by 2 root sigma C square plus 4 tau square. Okay, so the value of the sigma C maximum, it should be less than the allowable compressive stress. So if the value exceeds the allowable compressive stress, the width of the wave W can be increased. Okay, because it does not affect the other calculations. So we can directly increase the value of the width. Okay, and now the next, the design of shaft at the juncture of crank wave. Okay, shaft design. So let us, DS1 is the diameter of shaft at the juncture of crank wave. Okay, so the cross section of the shaft at the juncture of the crank wave is subjected to the different moments. Bending moment in vertical plane MBV, okay, due to the PR, and bending moment in horizontal plane MBH due to this load PT, and torsional moment MT due to the tangential component PT. So we have already known that MBV is equal to PR 0.75 LC plus T, and MBH is equal to PT 0.75 LC plus T, and MT is equal to PT into R. Okay, so therefore the resultant bending moment is given by MB is equal to root MBV square plus MBH square. Okay, so the torsional shear stresses in the shaft are calculated by this equation. Tau is equal to 16 pi ds1 cube. Okay, tau is equal to 16 pi ds1 cube root mb square plus mt square. Okay, where this tau is a allowable shear stress. Okay, so from this way you can design the shaft. Okay, now design of shaft under flywheel. So ds is the diameter of shaft under flywheel in millimeter. So as discussed earlier, the central plane of the shaft is subjected to maximum bending moment, and the bending moment in vertical plane mbv is equal to, given by this equation, PR into b plus c1 minus r1v plus r1 dash v into c1. Okay, and a bending moment in horizontal plane, that is the mbh, is given by mbh is equal to pt b plus c1 minus r1h plus r1 dash h into c1. Okay, from the figure first. So resultant bending moment mb is given by mbv square plus mbh square. Okay, and it is also subjected to the torsional moment. So it is pt into r. So therefore tau is equal to 16 upon pi ds cube root mb square plus mt square. Okay, so from this way you can find the diameter ds, or you can check, right? So by this way we can design the side crankshaft at a angle of maximum torque. Okay, so now I hope you can understand very well of the design procedure of the crankshaft, and in our next lecture you will learn about the design of the valve gear mechanism. Okay, so thank you very much, friends.